Because there is a high deviation of areas using the midpoint rule, trapezoid rule is a more accurate area determination method. Learn about it here in Numerical Solutions 2C problems. Before delving on the different methods, let's compare analytic and numerical integration in solving for areas. Say a function describes a curve and the area under is bounded by a and b. Exact integration utilizes integral strips with dimensions of y and d of x. The total area is then the integral of y dx or f of x dx from a to b to solve for the exact area. On the flip side, numerical integration then adopts the same concept of working with strips, but this time, the number of strips are provided instead of integrated. The area of each strip is solved and the summation is taken. The trapezoid rule still uses the concept of dividing the total area into the desired strips, but instead of rectangles, these strips are trapezoidal, the area of which require the two parallel sides to be known along with the base. That is half of the base multiplied by the summation of the two bases. After knowing the individual areas, the overall area would just be the summation of the individual parts. The function is then half of delta x times the first base plus twice the other bases within the area plus the last base. Let's simplify the working function first to easily apply it in examples. If a curve is provided and the area bounded by a to b below is to be determined, the approximate approach is to divide the area into smaller intervals, but taking more consideration with the curve on top, thus using trapezoid instead of rectangle. In case the area is to be divided into 4 parts, and each slice is denoted as B1 all the way to B5, the first trapezoid carries area 1, which is delta x over 2 times B1 plus B2. If the parentheses are to be taken out, the terms become half of delta x times B1 plus half of delta x times B2. The next trapezoid has an area of delta x over 2 times B2 plus base 3. The third trapezoid also has an area of half of delta x times B3 plus B4. This is simplified as half of delta x times B3 plus half of delta x times B4. The same is noted with the fourth area. A4 is then delta x over 2 of B4 plus B5, which becomes delta x over 2 of B4 plus half of delta x times B5. The total area is the summation of the individual trapezoids. So A total is half of delta x times B1 plus twice of the term delta x over 2 times B2. Then also twice of half of delta x times B3 and 2 times half of delta x times B4. Then finally, delta x over 2 times B5. Since delta x over 2 is common to all terms, extract it out and simplify the function for the total area as delta x over 2 times B1 plus 2 times B2 plus twice of B3, twice of B4, and end it with B5. The example using midpoint rule is also analyzed through trapezoid rule. The limits of the function provide the total base of the area, and the example shows 1.2 minus 0, which gives 1.2. With 4 intervals required, delta x is then 1.2 upon 4, which is 0.3. So there are bases on 0.3, 0.6, and 0.9. Knowing the x locations of the bases, solve for the heights. b1 is plugging 0 into the function and get 1. b2 is 2.5 times the square of 0.3 plus 3.75 of 0.3 plus 1, which results to 2.35. b3 is 2.5 times 0.6 squared plus 3.75 times 0.6 plus 1, which yields 4.15. b4 is 2.5 times 0.9 squared plus 3.75 times 0.9 plus 1, giving 6.4. The last base is 2.5 times 1.2 squared plus 3.75 times 1.2 plus 1, which is 9.1. With delta x and b's already determined, the functions then put to work, thereby having half of 0.3 times the long quantity of 1 plus twice of 2.35, twice of 4.15, 2 times 6.4, then add 9.1. The total area is then solved as 5.385.